Time crystals. Just saying the name feels like stepping into the realms of alchemy or science fiction. But these are real, tangible phenomena that challenge the very foundations of physics. Unlike ordinary matter, time crystals don't seek equilibrium. Instead, they defy it, existing in a state of perpetual, rhythmic motion through time. Their atoms cycle in a repeating pattern, not in space, but in time itself.
Right, and this isn't just some odd physics trivia. These things actually have huge implications. I mean, perpetual motion in time opens a lot of doors for quantum tech, doesn't it?
Indeed. What's particularly unique about time crystals is their ability to maintain this oscillatory state without consuming energy like traditional systems would. It's almost as if they exist outside the rules of the universe we know.
So, kind of like throwing the laws of thermodynamics out the window?
Not entirely, but I see where you're going. They don't break those laws. They operate in loopholes. And what makes the recent breakthrough at TU Dortmund so significant is not just the existence of a time crystal, but how long it lasted. Over 40 minutes.
Yeah, which honestly is like forever in the quantum realm. We're talking about a 10 million-fold improvement over what we had before. This beats the microseconds or milliseconds that previous models could manage, right?
Precisely. And the key innovation here lies in the material, indium gallium arsenide. This semiconductor, commonly used for electronic and photonic applications, provided the perfect environment for the time crystal to sustain its coherence. It operated at room temperature, which frankly is monumental for scaling quantum technologies.
Okay, hold on. Room temperature? That's basically the holy grail of quantum tech. Because usually you need these insanely cold environments, right? Like liquid helium cold.
Exactly. This advancement bypasses the logistical nightmare of cryogenics. The team at TU Dortmund achieved this by tapping into the nuclear spins within the crystal. Think of these spins as a sort of energy reservoir, maintaining the crystal's rhythm. Light was used to activate it, almost like flicking a cosmic switch.
So it's like this all-in-one self-powered oscillator that just keeps going. That makes it way more practical for things like quantum computing or even precision measurements, doesn't it?
Indeed. This brings time crystals closer to real-world applications. They could become integral to quantum systems, serving as robust tools for both computation and advanced sensing. But there's much more potential we've barely begun to explore.
Yeah, like the light activation mechanism. That's huge for control and integration, especially if you're thinking about scaling these things. Also, it definitely feels like this is where science is solving problems for itself, especially with combining simplicity and radical innovation in one go.
A fair point, Nova. What they've provided is a remarkable step forward, a glimpse into a quantum future where such phenomena become commonplace.
And I have a feeling we're just scratching the surface. Who knows what this tech could mean for error reduction in quantum systems, or even things like AI applications. You know what really blows my mind? This whole indium gallium arsenide breakthrough. It's not just a miracle material for time crystals sustaining coherence. It also hints at solutions for one of quantum computing's biggest challenges, reducing errors.
Ah, quantum decoherence, the eternal challenge. These systems are notoriously fragile. Qubits can lose their state from the slightest environmental disturbance. But embedding time crystals, stabilized thanks to indium gallium arsenide, could enable a kind of temporal scaffolding to preserve coherence.
Exactly. And when you minimize those errors, you're making a huge leap forward. That means better encryption, stronger AI systems. It's like completely upgrading our digital toolbox.
And not just limited to computation. Let's think about sensing. Rydberg atoms are also making waves in quantum technology, offering extraordinary sensitivity to electromagnetic fields. They're capable of detecting even the faintest electric signals while operating at room temperature. A recurring theme here, it seems.
Oh, I love this. Room temperature is starting to feel like the new frontier. But Rydberg, you mean those atoms that are souped up with crazy high energy states?
Precisely. Their exaggerated properties, such as massive dipole moments, allow them to pick up electromagnetic variations with precision beyond imagination. Picture them mapping microwave circuits or tracking radar signals with unprecedented accuracy. The implications for communication networks and even next-generation radar systems are staggering.
Whoa, hold on. So we're talking about tech that could map circuits, sense fields, and maybe even revolutionize radar? That's a game changer. Like, think about how this levels up everything from telecommunications to defense.
Indeed, this reminds me of pivotal shifts in history, the advent of electricity, or the dawn of the internet. Each catalyzed industries and reinvigorated societies. The technologies we're discussing have the same transformative potential on an even greater scale.
I totally get that. But hear me out, it's also kind of poetic. These things are bridging invisible worlds, time crystals manipulating abstract flows, and Rydberg atoms interacting with fields we can't even sense. It's like science is making the unseen, seen.
A fascinating way to frame it, Nova. They are instruments of revelation, tools allowing us to observe and control realms previously hidden from our perception. In doing so, they expand both technological and philosophical boundaries.
Isn't it wild how these invisible realms are becoming the foundation for visible breakthroughs? Like, we're not just tinkering at the edges anymore. Advancements like photonic circuits and timetronic innovations are accelerating us toward closing the gap between classical and quantum technology. High-efficiency light amplifiers, hybrid systems. It's hard not to feel like we're on the verge of something massive.
Indeed, Nova. Timetronic systems particularly intrigue me. By creating dynamic, temporal frameworks, they offer a method of organizing quantum components akin to the printed circuit boards of traditional computing. It's an elegant blend of the temporal and the tangible, almost alchemical in nature.
I knew you'd say that. But seriously, the possibilities here are wild. Imagine circuit boards made of time crystals that not only process quantum information, but reduce the errors that drive researchers crazy. It's like taking quantum computing from theory to an everyday tool.
Precisely. And this convergence doesn't end with computation. Consider the applications we've touched on: advanced radar, biological imaging, even ultra-precise timekeeping. Room temperature Rydberg systems alone could revolutionize entire industries. Their sensitivity to electromagnetic fields makes them invaluable tools for scientific exploration and surveillance technology alike.
And let's not forget healthcare. I mean, biological imaging that could detect early signs of disease or track cellular processes in real time. That's the kind of game changer that impacts all of us, not just researchers in labs.
It's true. These advancements could herald an entirely new paradigm in medicine and diagnostics. But with any transformative technology, there are questions that demand our attention. Questions of ethics, regulation, and balance. History teaches us that progress, unchecked, often leads to unintended consequences.
Right, and that's where society steps in, right? Like, how do we make sure the cool stuff doesn't spiral into the bad stuff? We're already seeing how tech often outpaces the rules we set for it.
Precisely, Nova. It brings to mind myths about humanity overreaching its grasp, Prometheus bringing fire, or Icarus flying too close to the sun. Both are warnings and aspirations, tales of ambition tempered by caution. Perhaps the lesson here lies in balance, progress coupled with mindfulness.
I like that. So, it's not about slowing down, but thinking forward. We're on the verge of turning science fiction into science fact. The question is, how do we shape it for good while keeping our feet on the ground?
Exactly. It's a crossroads of imagination and responsibility, a chance to craft a future worthy of our potential. And that, perhaps, is the greatest uncertainty worth exploring.
Well, on that note, I think it's safe to say we've barely scratched the surface today. There's so much more we could dig into, but for now, this feels like a good place to pause.
Indeed. Until next time, remember, Exploration begins with uncertainty, but it thrives on curiosity.
And curiosity's never boring. See you next time.